So today I'm going to talk about new developments in batch release testing, specifically sterility testing and the GMP sterility test. I'm going to cover the traditional GMP sterility test, what is rapid sterility testing, 3 different methods of rapid sterility testing, and also how you would conduct a rapid sterility validation. So the traditional GMP sterility test, it's conducted by direct inoculation or by membrane filtration, and this is to comply with GMP regulations and pharmacopoeial standards. In traditional testing, 2 different media are used, thiomedia and a soil-based media, and they would be incubated at 2 different temperatures. The sample is, of course, inoculated into this media, and the test is incubated for 14 days. However, if the sample itself creates a bit of turbidity and you cannot tell if it's a positive result or not, a subculture may be required, taking this to 21 days. But of course, this length of time, 14 to 21 days, it's a long period of time, especially in this industry, and it may not be suitable for products with a short shelf life or products prepared for immediate clinical use. A major disadvantage of the traditional sterility test is the subjectivity of the visual examination of results. Turbidity must be visually verified by laboratory personnel. You do get some machines that can electronically read sterility samples these days, but the traditional test is usually done with a visual examination of the final read. And if you look at these 4 samples, you can see how hard it can be to tell whether a sample is contaminated or whether it is just turbid. And this is especially the case with samples such as bulk harvests. In this case, actually, it's samples 3 and 4 that are contaminated. So what is rapid sterility testing? Well, these are tests that offer a faster alternative to traditional sterility testing. Rapid sterility testing methods work by reducing or even eliminating incubation times by using modern technology and automation to detect the presence of microbial contamination. So rapid sterility testing is acknowledged by both the European and the US pharmacopoeias in these chapters here. And it was actually first acknowledged by the European Pharmacopoeia in 2006. However, it's still not as standard, and as such, finding the correct rapid test for your product and validating it by equivalence testing with the traditional method is very important. Now, many rapid sterility methods have been developed over the past 20 years or so. So here's a few examples. You've got ATP bioluminescence, CO2, colorimetric detection, PCR, gas pressure detection, solid phase cytometry, flow cytometry, mass spec, autofluorescence, and you can see there's a massive difference in the time that these tests take compared to the traditional sterility test, which, 14 to 21 days. These are all less than 7 days. Most of them can be done within a day. The tests I'm going to look closer at today are those most promising for GMP validation. And those are ATP bioluminescence, CO2 or colorimetric detection, and finally solid phase cytometry. And this just shows that, compared to that 14 to 21 day traditional test, these rapid tests are really looking to get it done between 1 to 7 days, if not within the day. It's really important for your lot release and getting the product to your patient quicker. ATP bioluminescence is a well-established protocol for pharmaceutical products and raw materials. ATP bioluminescence uses luciferin and luciferase to break down microbial ATP from growing cells to produce light, and this light is detectable by a luminometer. The only thing with this test, though, is you have to really minimize the presence of non-microbial ATP. An example of a machine developed using this technology for GMP is the Merck Milliflex. This machine involves sample filtration. The filter contents are then placed onto agar, and then ATP releasing agents are added before the luciferin and luciferase treatment. A cell count is then reported, and there is an option for a longer growth stage, which is helpful because then you can have subsequent identification of your organism. Also available is the Charles River Celsius Advance. Now, the benefit of this machine is that your product can be processed by membrane filtration or by direct inoculation into the media. Medias are then incubated, and aliquots of both media types are placed in small cuvettes and loaded into the machine before the luciferin and luciferase treatment. The benefit of this is that you've got elimination of analyst interpretation. The growth phase, of course, adds time, but it does allow for subsequent identification. And there's a great flexibility in sample types. Suspensions, oils, anything that can be tested using the traditional sterility testing method can be used. But the good thing about both of these methods is they are non-destructive. You can still identify your organism at the end. And the disadvantage to both of these methods, of course, is that they both have a growth phase, which adds time to your test. So it can't be done in just a number of hours, but it's still a lot shorter than the traditional sterility test. Now, the colorimetric or CO2 detection method is another type of growth-based testing. This detection method relies on the color change being produced in a test media as a result of microbial metabolism during the growth. This often specifically applies to CO2 production, and this does limit the range of organisms that can be detected by this method. A common rapid sterility system that uses colorimetric detection is the BacT Alert. It was originally designed for clinical blood testing, but recently found its way into the pharma sterility setting. So the way this works is to begin with, your samples would be added directly to a liquid culture media by direct inoculation. There would then be a subsequent incubation period, and CO2 would be released. This CO2 diffuses into a colorimetric indicator at the base of the bottle. Hydrogen ions react with the sensor and lower the pH, resulting in a yellow color which is detected. The benefit of this is it monitors all your samples and all sensors every 10 minutes. And the great thing about this one is actually you can very easily scale it up because these are designed as individual units. And of course, again, with the growth phase detection, these are non-destructive methods. So it allows for out-of-spec investigations, subsequent identification of any bacterial contamination. And lastly, I just wanted to look at a non-growth based system. This one was also developed by bioMaru. Now, non-growth based systems do not rely on microbial growth to detect contamination, but instead use cell labeling techniques to detect and quantify viable organisms. They can detect a very wide range of organisms in a few minutes and very, very low levels of contamination, as low as 10 CFU. An example of this is the scan RDI. And the way this works is your product is filtered through the membrane, your test article, and any organism on the filter is labeled with a non-fluorescent substrate. In metabolically active cells, the substrate is cleaved to produce a fluorochrome. This is detected by a laser, and it ensures that only viable cells are detected. Also, any background noise is then rejected. Now, an advantage of this is it's very fast. It's the fastest method I've looked at so far. And you can detect, again, very low numbers of contamination, and it doesn't require a growth step. But along with this, there are some disadvantages. Of course, it's destructive, which limits any out-of-spec investigations and identification of bacteria. The results do need to be human checked, and your sample must be filterable. Like I said, not all of test articles and final products are going to be able to be filtered. And that's just a summary of the detection principle there. Now, the validation of rapid sterility tests. Rapid sterility tests must be approved on a case-by-case basis, and this is a risk-based decision. The patient safety is paramount. And some places still do not accept rapid sterility testing. We discussed when I originally presented this presentation that California does not accept rapid sterility testing. So you really have to be aware of the guidance in your area. And like I said, the rapid sterility test is still not as standard in the pharmacopoeia, so you have to conduct an equivalence validation. An equivalence validation is a validation to show that the rapid test you're gonna use is either better or equal to the traditional sterility test. So what do you have to validate? Well, you have to test the specificity, your limit of detection, the repeatability of the assay. Interestingly, you have to test for recovery of stressed or injured microorganisms. That's very important. And finally, you have to do a statistical analysis to ensure equivalence between the rapid test and the traditional test. So this image on the left here is just an example of a validation of the BacT Alert. And you can see there is adaptability in the machine. In the first run, they couldn't get A. brasiliensis to grow, but upon making adaptations to the protocol, the final validation was successful, and you can see at the bottom that the BacT Alert and the traditional sterility test are pretty much equal, and this was a successful validation. So in conclusion, rapid sterility testing is fast becoming a go-to for GMP industries looking for a faster, more effective and less subjective sterility test.